The inspector is correct in that the derating calculation should have started at 20 amps, not 30 amps. According to National Electrical Code Section 310.15b2, for more than 3 current-carrying conductors in a conduit, the ampacity of each conductor shall be reduced as specified in the code. The original derating calculation from 30 amps to 21 amps is incorrect. The correct calculation from 20 amps to 16 amps shows that the installation meets National Electrical Code requirements. The inspector's objection is valid. National Electrical Code Section 310.15b2 does not specify that neutral should be counted when determining the number of current-carrying conductors in a conduit. However, some interpretations of the code may suggest that neutral should be included. Now let's dive deeper into the specifics of this electrical derating scenario. The key issue revolves around correctly applying the National Electrical Code, or NEC, guidelines for derating conductors in a conduit. This is crucial for ensuring the safety and reliability of electrical installations, especially in environments like a gym where lighting demands can be significant. The problem centers on a gym lighting installation where 7 circuits, each feeding a maximum of 4 400-watt, 120-volt lights, were run in a single 3/4-inch electrical metallic tubing, or aimed conduit, using number 12 THHN wire. The initial calculation by the installer involved starting with a 30 amps ampacity for the number 12 THHN wire, derating it by 70% due to the number of conductors in the conduit, resulting in a final ampacity of 21 amps. Each circuit was then protected by a 20 amps breaker. The inspector, however, flagged this installation, stating that the derating calculation should have started at 20 amps instead of 30 amps. To understand why the inspector is correct, we need to delve into the relevant section of the National Electrical Code, specifically section 310.15b2. This section addresses the adjustment factors for more than 3 current-carrying conductors in a raceway or cable. When the number of current-carrying conductors exceeds 3, the ampacity of each conductor must be reduced, or derated, to account for the increased heat generated within the conduit. This derating is necessary because the more conductors there are, the more heat is produced, which can potentially damage the insulation of the wires and lead to electrical failures or even fires. Table 310.15b2 provides the derating factors based on the number of current-carrying conductors. For 4 to 6 conductors, the derating factor is 80%. For 7 to 9 conductors, the derating factor is 70%. For 10 to 20 conductors, it is 50%. And for 21 to 30 conductors, it is 45%. In this specific case, there are 7 circuits in the conduit, which means there are 7 current-carrying conductors, excluding the neutral conductors if they are not considered current-carrying under specific conditions, which we will discuss later. Therefore, the correct derating factor is 70%, as the installer initially calculated. However, the mistake lies in starting the derating calculation with 30 amps. According to Table 310.16 of the National Electrical Code, which lists the allowable ampacities of insulated conductors rated up to 2000 volts, number 12 THHN wire has an ampacity of 30 amps when used in dry or damp locations and rated for 90 degrees Celsius. However, there's a crucial caveat. The 30 amps ampacity is only applicable if the terminations and equipment are also rated for 90 degrees Celsius. In many common applications, especially with standard breakers and receptacles, the terminals are only rated for 75 degrees Celsius or even 60 degrees Celsius. When this is the case, the ampacity of the number 12 THHN wire must be based on the temperature rating of the weakest link in the circuit, which is typically the terminal rating. If the terminals are rated for 75 degrees Celsius, the ampacity of number 12 THHN wire is limited to 25 amps. If they are rated for 60 degrees Celsius, the ampacity is further reduced to 20 amps. Since it is highly probable that the breakers and lighting fixture terminals in this gym installation are rated for 60 degrees Celsius or 75 degrees Celsius, the correct starting point for the derating calculation is either 20 amps or 25 amps respectively, not 30 amps. Let's assume the terminals are rated for 60 degrees Celsius, which is a common scenario. In this case, the ampacity of number 12 THHN wire is 20 amps. With 7 current carrying conductors in the conduit, the derating factor is 70%. Therefore, the derated ampacity is 20 amps multiplied by 0.70, which equals 14 amps. This means that, after derating, each number 12 THHN wire in the conduit can only safely carry 14 amps. Now, let's compare this derated ampacity to the actual load on each circuit. Each circuit feeds 4 400-watt lights at 120 volts. The current draw of each light is calculated by dividing the wattage by the voltage, which is 400 watts divided by 120 volts, resulting in approximately 3.33 amps per light. With 4 lights per circuit, the total current draw per circuit is 4 lights multiplied by 3.33 amps per light, which equals 13.32 amps. Since the actual load of 13.32 amps is less than the derated ampacity of 14 amps, the installation technically meets the National Electrical Code requirements, even with the correct derating calculation. However, it's crucial to note that this is cutting it very close. Any slight increase in the load, such as using slightly higher wattage bulbs or having voltage fluctuations, could push the current draw above the derated ampacity, leading to overheating and potential safety hazards. Now let's address the issue of counting neutrals in the derating calculation. The National Electrical Code generally does not require counting neutral conductors when determining the number of current carrying conductors for derating purposes, with some exceptions. One exception is when the neutral conductor carries a significant amount of current, such as in a 3-wire circuit where the majority of the load consists of nonlinear loads. Nonlinear loads, such as electronic ballasts and fluorescent lights or switching power supplies in electronic devices, can cause harmonic currents to flow in the neutral conductor. These harmonic currents can increase the neutral current to the point where it becomes a significant heat source, requiring the neutral conductor to be counted as a current carrying conductor for derating purposes. In this specific gym lighting installation, if the lights are standard incandescent or LED lights without electronic ballasts, the neutral conductors would typically not be considered current carrying for derating purposes. However, if the lights are fluorescent lights with electronic ballasts, it's essential to evaluate the harmonic content of the neutral current to determine if the neutrals should be counted. If the neutrals are counted, the number of current carrying conductors would increase from 7 to 14, assuming each circuit has its own dedicated neutral. In this case, the derating factor would be 50% according to table 310.15b2. With a 50% derating factor and a starting ampacity of 20 amps for the number 12 THHN wire, the derated ampacity would be 10 amps. Since the actual load of 13.32 amps per circuit is greater than the derated ampacity of 10 amps, the installation would not meet the National Electrical Code requirements. In this scenario, several options could be considered to bring the installation into compliance. Firstly, the number of lights per circuit could be reduced to lower the current draw below 10 amps. Secondly, larger conductors could be used, such as number 10 THHN wire, which has a higher ampacity. Thirdly, additional conduits could be installed to separate the circuits and reduce the number of current carrying conductors in each conduit. Fourthly, the existing 3/4-inch EMT conduit could be replaced with a larger size conduit to improve heat dissipation. In conclusion, the inspector's objection to the initial derating calculation was valid because the calculation should have started with the correct ampacity for the number 12 THHN wire, based on the temperature rating of the terminals and equipment. While the installation technically meets the National Electrical Code requirements with the correct derating calculation, it is cutting it close. Furthermore, it's crucial to evaluate the harmonic content of the neutral current to determine if the neutral should be counted as current carrying conductors for derating purposes. If the neutrals are counted, the installation may not meet the code requirements, and corrective measures may be necessary to ensure safety and compliance. This scenario highlights the importance of thoroughly understanding and correctly applying the National Electrical Code guidelines for derating conductors, especially in installations with multiple circuits and high lighting loads. Proper derating calculations are essential for preventing overheating, electrical failures, and potential fire hazards.